Hello class, welcome to lecture 17, and in this lecture we're going to be covering some topics related to weather and climate as well as some subtopics related to those topics. So in this first segment we're going to take a closer look at the definitions of weather and climate themselves and also some statistical definitions that are related to weather and climate. So with that we'll go ahead and dive right into it. So first off, the whole idea behind weather is it's describing a short-term variation in some physical parameter or some measured quantity. So we're usually talking about a timescale on the order of a day-to-day variation or an hour-to-hour or even to some degree a minute-to-minute variation. That can also be described as something related to weather. But you could also potentially extend this out to say a week-to-week variation, but usually we're talking about some sort of day-to-day variation in some measured value or some physical parameter. An example of something weather-related would be the daily high temperature today being 96 degrees. So if we observe that the high temperature for this specific day in the calendar year is 96 degrees, that would be an example of something weather-related because we're looking at something on a short time scale. We're looking at what's happening on this specific day in the calendar year as opposed to looking at what happened several decades into the past, which is where climate enters the story. The whole idea behind climate is looking at the mean state of the atmosphere over a very long time period, usually on the order of several decades, but you could also theoretically go back even centuries and look at what the average state of the atmosphere was. And if we're looking at something, say, that's related to high temperature, we could look at the climatology of the high temperature, which basically is, if we go back several decades, look at every high temperature that occurred at this specific day, then we can add all those numbers up, divide by the total to get the climatology value or the average value. So if you say that the normal high temperature for today is 99 degrees, then that means if you go back all those decades, you take the sum of all those high temperature measurements divided by the total, you would get a value of 99 degrees. And this is often also referred to as the climatology. So if you hear the term climatology, then basically all you're doing is you're talking about an average. You're looking at an average that was taken across several decades worth of data. In fact, there's an old saying that goes something like this. Climate is what you expect, weather is what you get. So climate basically describes on any given day what is the average, what happens on average, what would be what you expect to happen most often. Of course, weather usually deviates from the average to some degree, so you don't exactly get what climatology is predicting, but you will get something that's usually pretty close. So in this specific case, where we have a normal high temperature of 99 degrees Fahrenheit, then an observed high temperature of 96, yeah, that's pretty close to climatology, so nothing too wild or too unusual is going on, versus maybe you have a high temperature of 80 degrees Fahrenheit and you expect a normal high of around 100 degrees Fahrenheit. Something strange definitely happened on that day. So that's sort of a representation of how unusual a particular observation or a particular measurement might be when we compare it to what we normally expect by normally expect, we basically mean how over a period of several decades, on average, what actually does happen on this particular day in the calendar year. And a mathematical representation of this is given by what's referred to as the anomaly. And if you took my METR2023 class, one of the projects or one of the tests on the final project was related to this idea of an anomaly where you take the observed value minus the climatology or the mean value, and that gives you your anomaly, which basically tells you whether you're above normal or below normal, and it also tells you how above normal or how above climatology you actually are, or how below normal or how below climatology you actually are. So again, this term x here is the observed value, the value that you're actually observed. So in this case, that would be this 96 degrees Fahrenheit. And this x with the overbar is your mean value, which would be your climatology, which in this case is 99 degrees Fahrenheit. And if we want to represent that by words, we can just simply say that the anomaly is equal to the observed value of a particular measurement minus the average value of the particular measurement. And if we want to do that for this specific case, then we take our observed value, which is 96, subtract it from our average value, our mean value, or our climatology. All those basically represent the same thing, and we get a value of minus 3 degrees Fahrenheit. And by the way we define anomaly, if you get a positive anomaly, that means you've got an observation that is above normal. And in this case, we had a negative anomaly, which tells us that our observed value is in fact below normal. So we got an anomaly of negative 3 degrees Fahrenheit, which basically tells us that our high temperature was below normal, which we can also confirm just by a visual inspection and using some basic logic. Now, there is a bit more that has to go into this anomaly calculation, because there are some values in the atmosphere that can vary quite vastly, and there are some values that don't vary much at all. So high temperatures, especially during the summer, those don't really vary that much from one calendar year to the next. Let's say June 30th, 2008, you get a high temperature of 99, and then June, the same day, the same day in June in 2009, you get a high temperature of 98, and then the same day in 2010, you get a high temperature of 100. You're not getting very much variation in the temperature. So it'd be nice if we can sort of add some more to this equation so that we can get a better idea of how unusual is this deviation from the mean. And that's where the idea of the z-score enters the story. It allows us to sort of diagnose whether this particular anomaly really is something far from normal, or if it's something that we can consider to be somewhat normal or relatively normal. And the z-score is defined as the anomaly divided by the standard deviation of the data. And we'll talk more about what exactly standard deviation is. Some of you may or may not have had statistics before, but we'll take a look at the definition of standard deviation and what it really represents. And if we want to substitute in the value that we have up here, we can get that the z-score is just equal to that particular observation minus the mean of all the observations divided by the standard deviation. And the standard deviation is represented by this lowercase s, and the mathematical definition for that is given by what looks like a very ugly equation, but it's really not that bad. The way that you calculate standard deviation is first you calculate what the mean value is. So let's say you've got a set of 10 different numbers. So first you have to calculate what the mean or the average is of all those 10 different numbers. And then for each one of those 10 numbers, you plug in, let's say we'll start with the first number, subtract it from the mean of all the numbers, take that value, whatever it might be, square it. And then you do that for the second entry. So say take the second entry, plug it into this equation, subtract it from the mean, square it, and then you add up all those square differences, all those square deviations from the mean, and then divide by 1 over the total minus 1. So if we've got a data set that has 10 entries in it, then we divide the sum of all those squares, we divide it by 9, and then we take the square root of the whole kit and caboodle. And we'll take a look at an example calculation involving this. But from a more practical standpoint, standard deviation basically represents how widely scattered the individual data points are. So if the data points are really, really far away from each other, then that would tend to tell us that we have a very wide distribution of data, which would correspond to a higher value of standard deviation, which means our term S here will in fact be quite large. And if we contrast that to, say, a data set where all the individual values are very close together, they're tightly grouped, there's not a whole lot of spacing between them, that would correspond to a lower value of standard deviation or a lower value of S. But just to sort of give you a better idea on how this works, we'll actually go through an example calculation. So let's say you've got a data set that's given by the set of numbers right here. So we'll say, just a super simple example, we'll take a look at 4 different numbers. So we'll say 90, 93, 100, 101. So we got 4 entries there. And the first thing that we have to do to calculate standard deviation, we have to first calculate the mean, which all we do to accomplish that. This is represented mathematically using fancy mathematical symbols and notation, but to calculate the mean, you just simply add up all the numbers and divide by the total, which is represented mathematically like so. And if we do that for this particular data set, we get that our mean is 96. So 90 plus 93 plus 100 plus 101 divided by 4 is in fact equal to 96. And now that we've calculated the mean, we are now in a position to where we can calculate the standard deviation. So again, then we just use this lovely equation. And if we expand this out, again, this is just sigma notation. And if we just expand that term out, we get that the standard deviation is equal to the square root of a massive line of numbers, square root of 1 over 4 minus 1, which is just 1/3, times first entry in the data set minus the mean, that whole quantity squared, plus the next difference squared. So we take the next item in the data set, which is 93, subtract it from the mean, take that difference and square it, and we add that to the difference we got from the first entry. Then we take the third entry in the data set, 100 minus the mean, take that quantity, square it, and then add that difference to the previous two, and then we continue that cycle on for until we get to the end of the data set. But here, since we've only got 4 entries, we go to the fourth entry, we get 101 minus 96 squared, and we add up all those square differences. So we take a difference and square it, we add up all those square differences, divide by the total minus 1, so we get 1/3 of this entire sum, and then once we take the square root of that number, we get that. In this particular case, the standard deviation of the data set is 5.35. But again, the whole idea behind standard deviation is it tells you how much your data is actually varying. Is it vary wildly, or do most of the values stay pretty close to a common point? And we take a look at how this affects the z-score. So standard deviation. So we have two parts of this. One is we have the anomaly itself. We have the deviation from normal, and the standard deviation tells us whether that anomaly is actually something to be considered an outlier or something that's really far away from normal, or whether we could consider that normal. And a general rule of thumb, if you've got a z-score that's greater than 2 or a z-score that's less than -2, that's usually when you start to think, okay, that value could be considered an outlier. Depending on, sometimes the statistics gives us a number, and then we, the human, have to go back and look at the data itself, see what was flagged as a possible outlier, and then say, yeah, we could consider that an outlier, or maybe we can't consider that an outlier. But usually, as a rule of thumb, if you get a z-score that's greater than 3 or less than -3, you're probably talking about an outlier. And by outlier, we mean a particular data point that is so far away from the average or so outlandish that it's basically something that's pretty unusual. So an example of that, again, we'll say high temperature. So go back to the example that we had earlier. So let's say we have a summertime high temperature of 99 degrees Fahrenheit. So let's say that's an average value for a particular day in the calendar year. And then we measure a high temperature of 65 for that same day in the calendar year. That's pretty unusual, and we would expect something like that to produce a pretty high z-score. But there are some physical parameters in the atmosphere that are naturally very they normally do vary a lot from year to year. An example of that might be monthly rainfall, especially in the spring. So when you go from the April of one year to April the next year, sometimes those rainfall values can normally vary by several inches. They can even, when you go from year to year, usually sometimes the values can vary by 5, 6, 7, or even 8 inches on any normal basis. If you starting to see variations of like 10 or 20 inches, then you might be starting to talk about a particularly unusual rainfall event. But one of the tools that we use to diagnose that is, in fact, the idea of the z-score. So we go back through all of our data, so over several decades, calculate the standard deviation of that, calculate the mean, and then once we get a particular observation or we have an event, then we plug that value in, calculate the z-score, and then get an idea of how unusual that event actually is. But that's going to do it for this first segment related to weather and climate. And in the next segment, we're going to introduce some more definitions as well as a brief overview of some of the stuff we're going to actually talk about in greater detail. So with that, I will see you all in the next segment.